Welcome back to ClearSpot. In 2024, the global solar industry lost $10 billion to asset underperformance. That's not equipment failure. That's not extreme weather. That's preventable performance loss hiding in plain sight, inside your data. The average solar facility lost $5,720 per megawatt last year alone. And here's what's alarming. Power losses have increased 214% over the past 5 years, from 1.84% to 5.77% of total capacity. I'm going to show you exactly why performance ratio is the single most important metric you're probably miscalculating, the 5 degradation pathways silently eating your revenue, and how to detect each one from your sensor data before it costs you millions. Let's get technical. Performance ratio, or PR, is the quality factor of your solar installation. Unlike capacity factor, which tells you how much energy you produced relative to the theoretical maximum, PR tells you how efficiently your system converts available sunlight into electricity. Here's why this matters. A solar farm in Montana and a solar farm in Arizona will have very different capacity factors, but their PR should be comparable, because PR normalizes for location, weather, and irradiance. The IEC 61724 standard defines performance ratio as PR equals YF divided by YR, where YF, final yield, is AC energy produced divided by rated DC power at standard test conditions. And YR, reference yield, is in-plane irradiation divided by reference irradiation, which is 1000 watts per square meter. In practical terms, PR equals your actual AC energy output divided by what you should have produced given the sunlight you received. According to IEC 61724 guidelines, above 80% means an efficient, well-maintained system. 80 to 85% is typical for modern, well-designed installations. And below 70% calls for immediate investigation. The best utility-scale facilities today achieve 85 to 90% PR. If you're below 80%, you're leaving money on the table. Here's where operators lose millions. 8 critical mistakes in PR calculation that can swing your results by up to 10 percentage points. The most common error? PR calculations depend entirely on accurate irradiance measurement. But here's the problem. Reference cell sensors and pyranometers give different readings. Reference cells measure irradiance in the plane of array, exactly what your modules see. Pyranometers measure global horizontal irradiance. Using the wrong sensor type, or worse, satellite data instead of ground measurements, creates systematic errors that compound over time. Another big mistake is ignoring temperature correction. Basic PR fluctuates 10% or more between summer and winter simply due to temperature effects. A plant passing PR tests in winter might fail in summer, not because performance changed, but because the metric is temperature dependent. The solution is temperature-corrected PR using the formula PR corrected equals PR nominal divided by 1 minus gamma times the cell temperature minus 25 degrees Celsius, where gamma is your module's temperature coefficient, typically negative 0.35 to negative 0.45% per degree Celsius. NREL's methodology shows temperature correction eliminates seasonal bias and provides consistent year-round measurements. Now here's an uncomfortable truth. It's not in your O&M contractor's interest to clean irradiance sensors. The dirtier the sensor, the lower the measured irradiance, and the easier it is to meet PR guarantees. Sensor calibration drift, incorrect positioning, and equipment degradation all contribute to measurement errors of plus or minus 5% or more. PR calculations also become unreliable at low irradiance levels. Below 700 watts per square meter, measurement noise dominates the signal. Best practice is to filter out periods below this threshold and exclude nighttime, heavy cloud cover, and transition periods. And let's not forget about clipping losses. When your DC array produces more power than your inverter can convert, you experience clipping. This is intentional in well-designed systems. A DC to AC ratio above 1.0 means some clipping will occur. But if you're not accounting for clipping in your PR analysis, you're comparing actual output against a theoretical maximum that was never achievable. Clipping losses are typically 1 to 3% at project start and decrease as modules degrade. Every solar panel degrades. The question is, how fast and why? Modern crystalline modules degrade at an average rate of 0.5% annually, meaning approximately 88% capacity at year 25. But you know, this average hides enormous variation based on technology, climate, and installation quality. Light-induced degradation, or LID, occurs in the first few hours to days of sunlight exposure. Oxygen traces in silicon wafers interact with boron dopant, creating defects that reduce efficiency by 1 to 3%. This is expected behavior. Manufacturers account for it in power ratings. But if you're measuring performance against nameplate values without accounting for LID stabilization, you'll see phantom underperformance. The best way to detect this is to compare initial commissioning output to day 30 output. LID should stabilize within the first year. Potential induced degradation, or PID, is far more severe. It occurs when voltage differences between solar cells and the module frame cause ion leakage, essentially electrons escaping where they shouldn't. PID can reduce panel performance by 20 to 30% or more over 5 to 10 years. The worst part is that it's often invisible until significant damage has occurred. Risk factors include high humidity, high system voltage, like 1000-volt systems, poor grounding, and certain module constructions. To detect PID, look for non-functional black cells near the frame in electroluminescence imaging, and monitor for abnormally low string voltage or current compared to parallel strings. LTID, or light and elevated temperature-induced degradation, is the hidden killer of PERC modules. Field testing has shown degradation rates of 6 to 10% in just 3 years for susceptible PERC panels. That's 10 times worse than the expected 0.5% annual rate. The mechanism involves hydrogen-related defects that activate under high light and high temperature, exactly the conditions where solar farms operate most of the time. Risk factors include P-type PERC technology, hot climates, and high irradiance locations. Detection involves monitoring long-term performance ratio trends. LTID shows gradual persistent decline beyond normal degradation. Some recovery can occur, making it honestly pretty difficult to distinguish from seasonal variation without multi-year data. Physical and mechanical degradation includes microcracks, hotspots, bypass diode failures, and cell damage. Microcracks can occur during manufacturing, shipping, or installation. They may not cause immediate power loss, but they grow over time due to thermal cycling and weather stress. GreenSolver reports that 2 to 3% performance loss is common from microcracks alone. Hotspots form when one cell operates hotter than adjacent cells, often due to shading, manufacturing defects, or prior damage. They accelerate degradation and, in extreme cases, create fire hazards. Detection methods include thermal imaging, where hotspots appear as localized temperature, increases of 10 to 20 degrees Celsius above surrounding cells. Electroluminescence, where microcracks appear as dark lines or areas where current flow is interrupted. And IV curve tracing, where abnormal curve shapes indicate cell-level issues. Environmental degradation includes soiling, corrosion, backsheet failure, and encapsulant degradation. Soiling alone causes 3 to 5% global annual energy loss, representing 3 to 5 billion euros in lost revenue. In desert or industrial environments, losses can reach 5 to 10% or higher. Backsheet failure affects 9 to 16% of modules and is a leading cause of premature failure. When the backsheet fails, moisture enters, accelerating corrosion and delamination. Detection methods include soiling sensors or clean reference strings for soiling quantification, visual inspection for backsheet cracking, yellowing or delamination, and string-level current monitoring for gradual decline patterns. Your monitoring system is collecting terabytes of data. So, here's how to turn that data into actionable degradation detection. String monitoring units measure voltage, current, and temperature at the string level. Compare strings in similar conditions. If you see a sudden current drop in one string, it could be a fuse failure, a disconnected cable, or major module damage. A gradual current decline across all strings, that's usually environmental soiling or systematic degradation. Voltage anomalies might indicate PID, bypass diode failures, or cell cracking. different degradation types leave distinct data signatures. For example, with soiling, voltage remains stable, current is reduced, and there's a linear decline with irradiance in power. PID shows reduced voltage and current with an accelerating decline in power. Hotspot or cell damage leads to slightly reduced voltage, a localized current drop, and step changes in power. If a string disconnects, both voltage and current drop to zero, resulting in complete power loss. Infrared inspection identifies issues invisible to electrical monitoring. Hot cells, those with more than a 10 °C differential, suggest a cell crack or manufacturing defect. If you see hot substrings, like a third of a module heating up, that's likely a bypass diode failure. Full module heating, with no current, points to string disconnection. The module absorbs irradiance but produces no current. Machine learning algorithms can analyze historical patterns to detect emerging degradation before it becomes critical. The key is establishing accurate baselines and continuously comparing actual performance against expected behavior given current conditions. String abnormality detection systems can identify 7 or more distinct fault types by analyzing voltage and current patterns at high sampling rates. How do you know if your performance ratio is good, bad, or just average? Benchmarking against industry standards provides context. For system age, the benchmarks are Year 1, 82 to 87% after LID stabilization. Year 5, 80 to 85%. Year 10, 78 to 83%. And by year 20 or more, 75 to 80%. Looking at degradation rate benchmarks by technology, PARC modules show 2% in year 1, then 0.45% per year. TOPCon modules have 1% in year 1, then 0.4% annually. HJT, or heterojunction technology, sees 1% in year 1, then 0.3% per year. And XBC, or back contact technology, has 1% in year 1, then 0.35% per year. Climate significantly affects degradation and performance ratio. Hot and humid climates mean higher PID risk and accelerated LTD. Hot and dry climates lead to higher soiling losses and thermal stress. Cold climates experience snow losses but reduced thermal degradation. Coastal sites face salt corrosion risk. Temperature-corrected performance ratio eliminates much of this variation, allowing meaningful comparison across sites. Here's the bottom line. Performance ratio is your most powerful diagnostic tool, but only if you calculate it correctly, understand what drives degradation, and know how to detect problems in your data. The 5 degradation pathways, LID, PID, LTD, physical damage, and environmental factors, are predictable. They leave signatures in your sensor data. The question is whether you're equipped to see them. This is exactly what AI agents are designed to solve. Instead of manually analyzing thousands of data points across hundreds of sites, intelligent systems can continuously monitor performance ratio trends, detect anomalies, correlate thermal and electrical data, and prioritize interventions based on revenue impact. At ClearSpot, we are building the autonomous intelligence layer that transforms passive monitoring into proactive optimization. Because in a world where $10 billion is lost annually to preventable underperformance, the farms that survive will be the ones that see problems before they become expensive. If you found this valuable, like, share, and subscribe for more solar insights. ClearSpot. Smart device, smarter decisions.